Okay. Welcome, everyone, to the 91st meeting of New Directions in Group Theory and Triangulated Categories. Today, our speaker is Casacuberta from the University of Barcelona, and he'll be talking to us about homotopy. Well, the title of his talk is Homotopy Reflectivity is Equivalent to the Weak Vopenka Principle.
Well, thank you very much, Rudadi. Well, first of all, thank you very much for the invitation. It's a real pleasure to be able to communicate these results. I apologize for some people in the audience who already heard the talk. I must say that I tried to adapt it to the audience. So this one is not addressed to set theorists, it's not addressed to topologists, but, well, to say it's a little bit of everything. And therefore, I will find a few things which you probably know, and I will give some details which I hope are comprehensive to everybody who is interested. So let me start by mentioning an older result. So we had that paper with Javier Gutierrez and Rosicky in the advances in 2014. And actually, most of the statements and concepts are symmetric, although in today's talk, I will concentrate on, I must say, colocalizing, and for the reasons that you will see. But so to say, several things are naturally symmetric, and now our paper with Javier and G, well, it dealt with reflections into colocalizing subcategories and also co-reflections onto localizing subcategories. And the results were symmetric, but the proofs were not. I'm just telling philosophically what the thing was, and I've selected just one theorem from that paper, which is going to be improved in today's talk. And so I'm talking about triangulated categories with models, actually locally presentable models. And under a suitable set theoretical principle, which I will shortly explain in a few minutes, then all full subcategories closed under products and fibres are reflective. I mean, being closed under products and fibres is necessary to be reflective. I will explain these things in a moment. And if you put appropriate set theoretical assumptions, it's sufficient. For this, of course, the fact that the model category is locally presentable is the clue, because of Vopenka's principle, as I will explain in a moment, it has to do with locally presentable categories, definitely. I don't claim having any theorem for triangulated categories without models. Then I read here, because I will mention these concepts. If the subcategory is semi-colocalizing, I'll define it in a minute, then the reflection is semi-exact. And if the subcategory is colocalizing, then the reflection is exact. So this was proved that about 10 years ago. It was a paper about triangulated categories, mostly. Although, again, all these notions can be formulated more generally, and I will define some of these notions more generally, like reflections. I mean, the language of reflections and localizations is much broader than the triangulated world, but as I say, I keep adapting my talk to the audience, and today I'm focusing really on triangulated categories for most of the talk. So reflectivity, I think you can see my cursor. Reflectivity, it's just another name given to localization. It's the fact that the reflection, well, typically it's going from the category to the subcategory. Sometimes what you want to do is to compose it with an inclusion and have a self-functor of a triangulated category. I will not really make a distinction among the two. Typically, a localization would go from T to T, while a reflection would go from T to L, but that's not really relevant for what follows. So let me now define all those things for people in the audience who are not familiar with this. I'm not talking of triangulated subcategories. That's the main thing I have to say. I'm not talking of triangulated subcategories. So I have to make some distinctions between being closed under fibers. So a full subcategory of a triangulated category is closed under fibers. If in every triangle where Y and Z are in L, then X is also in L. Of course, there is a symmetric notion, closed under cofibers, means that if X and Y are in L, then Z is in L. Also, closed under extensions, if whenever X and Z are in L, then Y is in L, and if all these things hold, then it's triangulated. Triangulated subcategory. If any two in a triangle are in L, then the third is also in L. I think this is clear enough. And the names for colocalizing and localizing, they're a little bit misleading because somehow the co is misplaced, right? One calls colocalizing when it is triangulated and under product. And one calls it localizing when it's triangulated and close under co-product. And well, the reason is that because the origin of this terminology in triangulated categories, somehow localizations were thought, let's say, on the left-hand side, on the acyclics. So to say, if we speak of homological localizations, then the localization was something thought on the part of the acyclics, and of course the classes of acyclics are closed under coproducts, and the classes of locals are closed under product. So how the terminology got reversed for historical reasons, I will not change that. I will add semi in front of the word when we only require closureness under products, fibers, and extensions. This is semi-colocalizing, and semi-localizing is closure under coproduct, cofiber, and extension. So you see that one of the things, either cofibers or fibers, is missing when we put here semi. And you will see, I will give examples in 2 minutes, and then you will see where the semi-colocalizing examples come and where the colocalizing examples come, at least from topology. I will give examples coming from topology. Also, a reflection, let's say, assuming that it goes from the triangulated category onto some full subcategory, it's called semi-exact when the target is semi-colocalizing, and it's called exact when the target is colocalizing. For those of you who know about localization, you should think of L as a class of local objects for some localization. Okay, I think if anything is unclear, just interrupt me. I assume this is mostly well-known and more or less a standard terminology. Also some basic, very basic facts. Yeah, the localizing things tend to be closed under cofibers, and the co-localizing and the fiber suspension match that. So in a semi-localizing category, then it's closed under retraction. Retraction is a technical thing which follows from the other assumptions, and also suspension. And when you take the semi-colocalizing, then you get desuspension. So just remember what is here the way of thinking. So the semi-localizing things are classes of cyclics with respect to something. So they indeed they are closed under suspension, while the ones where the co, those are the local objects, and those tend to be closed under suspension. And not reciprocally, not reciprocally. Well, of course, when both things happen, I think that Amnon Neyman calls these triangulated functors. So triangulated reflection is one which has all the closure properties that you want. It's closed under suspensions, it's closed under desuspensions, and the functor sends triangles to triangles, and all this is also equivalent to claiming that it commutes with suspension, so up to isomorphism. You don't have to assume it natural. It follows, naturality follows from the properties of localization. So reflection is exact. L sigma of x is isomorphic to sigma L of x for every x. And then, well, semi is less well known. Semi means what is explained here. That's that small theorem. Remember that being semi-exact means that the target category is semi-colocalizing, and the effect when you apply something semi-exact on a triangle, in general, you will not get a triangle. I'll show you an example next, the next slide. But the base of the triangle is in L, then it does. Of course, if the base of the triangle is in L, then putting LZ is the same as putting Z. And remember that L is to be thought of the local objects of some localization. So semi-exact means that all triangles are only guaranteed to be preserved when the base is local, while exact reflections preserve all triangles whatsoever. And I think that's enough for terminology. I hope I didn't confuse you with the co and with the semi. So here's an example. Here's an example. Well, actually a family of examples, and these examples somehow motivate what we do. I'm a topologist, so we thought of a spectra on the first instance, although this is much more general, so in the homotopy category of a spectra, then the homological localization, it means localizations which invert formally the equivalence of homology theory, they are exact. They are exact. They commute with suspension. They preserve triangles. However, Poznikov sections are also localizations. I'll say it how, but those are not exact. The Poznikov sections don't triangles in general. I'll show you an example there, but they are semi-exact. And well, Poznikov sections, which are well known, is just a special case of localizing with respect to a map between spectra. So actually, this is my favorite theory when we localize in the homotopy category of spectra with respect to a map. If it's any map whatsoever, then it's just semi-exact. It's always semi-exact, but only semi-exact. If you want an LF to be exact, then you have to ask more on F, typically that there is a wedge of suspension, or at least that a negative so that the suspension of F are retracts of F. And this is what happens actually with a map defining homology localization. And that condition, even if it may seem clinical, it holds in many examples. And that's precisely what you, not precisely, that's a sufficient condition that you need in order to have these as an exact factor. Of course, the Poznikov section does not have this property. It's localization with respect to a map of a certain suspension of the sphere spectrum, and of course, depending on n, you will have different properties of the corresponding localization. It will never be exact, but it will be, so to say, exact on a certain range depending on n. And here's an example. So maybe all the names which I've been giving so far will become clearer. The Bn is for Poznikov. It's for Poznikov. So when you take a Poznikov section of a spectrum, if it's the nth Poznikov section, it means that you keep all the homotopy groups in dimension n and below, and you killed everything in dimension n plus 1 or above. I repeat, so an n Poznikov section, Pn, preserves the homotopy up to dimension n, including n, and kills the higher homotopy groups. That's the effect of Pn on a spectra. Then this doesn't preserve fibrations in the category of a spectra, and to see why, assume that you are given a triangle where the n plus first homotopy group is not a surjective. Any example where this map is not surjective. Then I claim that the Poznikov section does not preserve the exactness in the sense that this is not a triangle anymore. This is not a triangle anymore. And to see that this is not a triangle, let's compute homotopy group. So if you compute homotopy group of the above sequence, you see that somehow the co-kernel of that map, which we are supposing that it's not a surjective, co-kernel will affect the remaining part of the long exact sequence. However, if this were a triangle, that would also have to be exact. But now, what is here on the left is the d-suspension of P and of B. So actually, you get a group 0 because that's Poznikov as an n Poznikov section, which has vanishing pi n plus 1. So there is a 0 here. So those two sequences cannot be both exact. This means that if you started with a triangle, what you get here is not a triangle. However, remember the condition. For being semi-exact, it's enough that B be in the image of the localization. B being in the image of the localization precisely means that this has to be 0. This has to be 0. If B is already a Poznikov section, then pi n plus 1 of B is 0, and then everything works. Everything works. So Poznikov sections are semi-exact, but they are not exact. That's my main example, and I hope this is clear enough. You can generalize these to other maps of a spectra, and so on. Okay. Now today's talk, so what I said so far was explaining my former theorem, the one in 2014 with Javier and Yirji. So now we have a preprint, which I hope it's going to be in the archive very soon, because the paper has already been around for some time, but there's always something we keep changing. And you see that it's very similar, a statement. So having full subcategories closed under product of fibers, that's exactly the the same thing that I showed in the previous theorem, homotopy category of a stable, locally presentable model category. But here we have an even only if, and that's the novelty. So the former theorem said that under Vopenka's principle, you would have reflectivity. Now we claim that reflectivity is equivalent to the weak Vopenka principle. I will define all these things in a moment. Not very technically, I hope, but I will define all these things in a moment. And I'll tell you what is the difference between weak Vopenka and Vopenka. And now our claim is that this is even only if. It's even only if, so it means that the statement that two subcategories close on the product of fibres in a triangulated category of locally presentable models is precisely equivalent to the weak Vopenka principle. Of course, this happens very often in many theorems which are implied by Vopenka. Those of you who are familiar with these things know that Vopenka's principle implies the existence of many things. But it's very difficult in general to get reverse implications. So you get that under large cardinal something happens, but in many cases you don't know that this is purely set theoretical. Actually, we knew already that the reflectivity of this kind of full subcategories was set theoretical, but we had a gap between them. Now we know exactly what is the large cardinal strength of that claim. In particular, this is something which is not provable in Zermelo-Frankel, because you know that all these large cardinal principles cannot be, you can prove that they cannot be proved in Zermelo-Frankel. So my job today is tell you a proof, to show you the concept involved in that theorem, to give you a proof, and then make some comment about what is not known. Okay, so let's go for that. Let me begin a little bit more general. So all that was in the language and framework of triangulated categories, but now I want to define orthogonality. And for that, I don't stick to triangulated categories, mostly because, I want to work I would say, in the framework of model categories. I will not use any machinery from model categories, but I want somehow to think in triangulated categories with models. So I don't want to speak of model categories, but just to be to say up to date, I chose to define it in terms of infinity categories. So an infinity category, just anything which is enriched in homotopy types. And in any infinity category, it makes sense to speak of map. Those maps will be infinity group points. It depends on your model. Take your favorite model of infinity categories. Those will be infinity group points. And then immediately you have a notion of orthogonality between objects and morphisms in any infinity category. I use this notation for orthogonality using that infinity group point enrichment. If you don't like to think of infinity group points, then you may be safer by thinking of a category enriched in Kant complexes. I mean, some models of infinity categories are enriched in Kant complexes, like quasi-categories. You may want to think of quasi-categories if you want, or in particular, of course, spaces, etc. And then a morphism and an object are orthogonal. And then, well, if the category is enriched in Kant complexes, you know what map Bx and what map AX mean precisely, and then that mysterious map of infinity group points is simply a composite of things that you can define in terms of little sets. Right? In any case, the orthogonality is defined whenever you have enriched categories where it makes sense to speak of homotopy types of mapping spaces. Again, this is quite standard, so that's our definition of orthogonality. And that's also terminology which is quite well known for a class of morphisms in any infinity category, in particular spaces or spectra. Just denote the orthogonal of a class of morphisms by the class of objects which are orthogonal to them, and conversely, this is totally symmetric. And then an S localization, so localization with respect to a class of morphisms of an object, is a morphism for which the target is in the double perp and the map is in the perp. And well, we call accordingly the maps in S perp as equivalences, and the morphisms, the objects which are image of L, we call them as local, and the maps which are in S perp, we call them as equivalences. In some sense, as equivalents are saturated. It's a kind of saturation of F under taking this double pair notation. It makes sense anywhere where you have kind of simplicial enrichment. And well, I'm not going to use any machinery from infinity categories in the talk, I'm sorry. I'm not going to use any machinery or almost any machinery from model categories in the talk. Actually, what I want to say is just that I use this for the definition, but I'm thinking of reflection onto the homotopy category. Now, I don't assume it's stable, just I work in the homotopy category of any infinity category, and I claim that the S localization as I just defined is the same thing as a reflection onto the S-perp in the homotopy category. And if you want, if you don't believe that, and you want this to be more precise, let me state it. So let's assume that we work in a category enriched in complexes, and tensor or cotensored over simplicial sets. Then, for a class of morphisms, given morphism is an S localization of X, even only if it is a reflection onto the S-perp on the homotopy category. Any category which is enriched in complex has an associated homotopy category where you simply take connected components of the mapping spaces, pi naught. And well, this is a bit technical, but it's written to prove simply an equivalence with equivalence of mapping spaces in any infinity categorical context as a bijection of pi naught of connected components. One implication is automatic. And for the converse implication, which might sound a bit surprising even to specialists, it's simply because now we have to infer a weak equivalence of mapping spaces with an assumption which only involves pi zeros. It seems that would be too much, but it's not, because to detect weak equivalence, you can simply use maps from any simplicial set. And now, map is a simplicial set, actually complex. So by using any simplicial set to fire to it, and using a couple of standard adjunction arguments, those two statements are equivalent. So you think here in the model category, in the infinity category, or just go down to the homotopy category, and again we are just led to thinking of reflection. And actually, my theorem and proof has to do with homotopy reflection. As I told you, we are not using any infinity category machinery in the arguments. Simply mentioning that, well, of course, the source of infinity categories is simplicial model categories. Those are enriched, those are automatically enriched on simplicial sets. And if you take the full subcategory of fiber and cofiber top, and the homotopy category, as I described it, is precisely the one which you get by taking pi naught in the mapping spaces. And those things are quite well known. So for a simplicial model category, if it's left proper and combinatorial, then sets of morphisms admit localizations. While proper classes, we don't know. That's of course the full story behind that talk. So for every set of morphisms, every class has a localization. And if you want to replace set by class, then you need to assume, for example, Vopenka's principle. And this was for simplicial model categories by Rosicky and Toland already a long time ago. And it also essentially the same result with different arguments you can find in a paper of mine with Boris Chorny in 2006. But this is well known. This is well known. And again, morally, what I'm going to do is the same thing I mentioned before. So Vopenka principle implies reflectivity in the case of classes of morphisms. Now I want to give an even only if, replacing Vopenka by weak Vopenka. That's my plan. I hope all this is clear enough so far. Insist if I'm going too fast or I say something strange, feel free to interrupt. So Vopenka, with Vopenka, what are all these things? So maybe now it's time to define these things. There are many ways to define Vopenka. One way is saying that the class of ordinals, or means the class of ordinals, and I'm assuming we work in Zermelo-Fraenkel. Everything is, our set theory is Zermelo-Fraenkel. Vopenka, as Vopenka himself stated, now with Jan we were commenting that he really didn't intend to build a large cardinal principle, but it became a large cardinal principle which people nowadays trust, but of course it cannot be proved. It cannot be. It could be inconsistent. It could be inconsistent. I think Jan will correct me afterwards, but I think Vopenka thought it was inconsistent, in fact. But it's never been proved to be inconsistent. And the fact that the class of ordinals cannot be fully embedded into any locally presentable category. And, well, if you don't know the definition of a locally presentable category, sorry that I used this word before without defining it. It's here, it's something which it's co-complete, it has co-limit, and somehow it's generated by a set of presentable objects of some order, lambda, where lambda is a regular cardinal, and being lambda presentable, that's essentially the same thing as in triangulated categories, kind of compactness condition that the functor from X preserves lambda filter co-limit. So those are the kind of categories which don't admit full embeddings of the class of ordinals according to Vopenka's principle. And then the weak, it's just inverting. Say, hey, why is this weaker? It's a different thing, right? You simply reverse the order of the sequence of ordinals, and then it should be a different thing. But of course, this is from the Prague school, at least 40 or maybe 50 years ago. That thing implied. So Vopenka principle implies a weak Vopenka principle. And at the time, I don't think it was known whether this was the same or not. It's been an open problem for many years, actually, until 2020. I'll tell you in a moment when and how this was elucidated, but let me reformulate it. Let me reformulate it. I will state Vopenka's principle with different words and weak Vopenka, and I will add something which is called semi-weak Vopenka. I'll tell you a word about semi-weak Vopenka. Right now it can look a bit technical. So this is essentially the same definition I gave in the previous slide. Vopenka says that there is no sequence of objects indexed by the ordinals in a locally presentable category. Well, of course, that sequence has to be a full embedding of ORD, and being a full embedding of ORD, it means that there can't be any morphisms going from up to down, and there should be only one going from down to up. That's the full embedding of ordinals. That's essentially Vopenka. And changing Vopenka by with Vopenka is reversing the signs. There can't be any sequence of objects in a locally presentable category indexed by the ordinals without any maps going now from small to large, and only one going from large to small. So this is a different way. It's rather symmetric in this sense, but it's opposite, you see. And then semi-weak, I'll tell you a little bit of the story of semi-weak Vopenka. I'll tell you where it came from. It replaces one by some. You see that semi-weak, it's the fact that there are no maps going from lower to upper, but there can be more than one going from upper to lower. So somehow, it seems that semi-weak Vopenka implies, it's a stronger. Semi-weak Vopenka is stronger than weak Vopenka, if it's stated this way. And a little bit the way semi-weak Vopenka was discovered was that, well, Adamek and Rosicky already in 1993 proved that chain of implications. Vopenka, semi-weak Vopenka, weak Vopenka. And well, the reason for semi-weak Vopenka was this was the kind of argument they needed. So for in some of the uses that Adamek and Rosicky were doing of this theoretical axiom, they didn't need the full strength of Vopenka. They realized that they had enough with what they call semi-weak Vopenka. But at the time, they didn't have the slightest idea of whether these three things were equivalent or not. And this was settled in 2020 by Trevor Wilson. That was really a breakthrough in this context. And Trevor Wilson proved that semi-weak and weak is the same thing. They are equivalent. And they are not equivalent to Vopenka. So definitely Vopenka is a stronger large cardinal assumption than semi-weak Vopenka. This is Wilson's theorem, was published in the Advances 2020. for you to get a little bit of a feeling of the difference between Vopenka and with Vopenka, I wrote here a category theoretical formulation. So Vopenka, maybe you like more that way of defining it. Vopenka is equivalent to the statement that every orthogonality class, remember the pairs in my previous slides, that every orthogonality class in a locally representable category is a small orthogonality class. A small orthogonality means orthogonal to a set. Orthogonality class is orthogonal to any class, to some given class of maps. Small orthogonality means generated by a set. So Vopenka somehow tends to produce sets of generators. So in every context where Vopenka gives positive results, you are seeking for a set generating something. If your assumptions are suitable, Vopenka tells you that there is this set generating something. While Vopenka is about reflectivity, and this was known already in the earlier papers of Gutierrez and Rosicky. So Vopenka is equivalent to the statement that every orthogonality class in a locally representable category is reflective. Of course, you know that. Those of you who like this kind of category theory development, you know that when something is generated by a set, it's reflective. That's the reason why Vopenka implies weak Vopenka, but not conversely. And then semi-weak is in between. Then it's not about orthogonality classes, it's about injectivity classes, and it just leads weak reflections. But that's very important because now I'm going to prove our theorem, and you will see that the concept of weak reflection is very relevant. And actually, semi-weak Vopenka tends to produce weak reflections. So while weak Vopenka tends to produce reflections, semi-weak tends to produce weak reflections, and it was known again many years ago. Actually, fact was used I mentioned at the beginning a paper of mine and with Gutierrez and Rosicky 2014. What we used was not Vopenka, was semi-weak Vopenka. We didn't mention at the time, but we were really using semi-weak Vopenka in the argument. And the argument was essentially the same that I'm going to show you now. So here's what we do. I repeat, this is the scope of our current paper. Every of the following things is equivalent to weak Vopenka, hence to semi-weak, because we know by Trebor-Wilson that weak and semi-weak is the same. Localization with respect to any class of map exists in the homotopy category of simplicial sets. Localization with respect to any class of maps exists in the homotopy category of spectra. It doesn't matter whether you work with simplicial sets or spectra. And here's the thing which I wrote in the abstract, because this was a seminar talk on triangulated categories. Every full subcategory was on the product of fibres in a triangulated category. Local representable model is reflective. Of course, you will say that, oh, this follows from you said before. No, because unfortunately, those are statements about homotopy categories, and homotopy categories are not locally presentable. This means that those results are to be expected, but there's a lot of technical work to be done. Okay, so I mentioned what is a weak reflection. A weak reflection is just half of a reflection. You don't assume that the arrow from X star is unique. So you assume that every map from X to B, if it is a weak reflection, or if X star is a weak reflection, every map from X to a member of the class will extend to X star, but not uniquely. This is a weak reflection. And then the theorem is that under semi-weak, every full subcategory close on the product is enough to assume products. It's enough to assume product is weakly reflective. That's our first theorem, and that's in a spirit the same that we proved with Xavier and Dirji 10 years ago. Well, the proof is here, and I really don't give any credit to us, because it's the same proof, which was that proof was the one which came after the introduction of semi-weak by Gutierrez and Rosicky. I will go quickly through the proof. I don't want to go slowly because maybe too technical. If you are interested, I'll send you our preprint. What you do is you work with the cumulative hierarchy of sets in Mello-Frankel. So V is the set theoretical universe, and then somehow you filter it by the ordinals. In VI, you get all the sets of rank smaller than I. Not exactly cardinality, it's rank to be precise. And then when you are given a full subcategory close on the product, what you do is to filter it again. You filter your full subcategory by taking things of rank smaller than I, and then you close it you close it and the product an isomorphism. This is a set. AI is a set, but when you take the closure and the product an isomorphism, it's no longer a set. This can be a proper class. You have to be careful, but it's generated by a set in that sense, and the product an isomorphisms. Then for any object in your category and every ordinal, you take the product of all the objects. You can do it because it's a set of the comma category going into. So we want to. Ultimately, we want to get a reflection onto T. Now we are getting only a weak reflection, and for that it's enough to take the product of all the objects in AI. That's enough. That's enough, and you can easily supply probably the details by yourself, because every object in the I is a product or isomorphic to a product, and then every morphism is determined by a collection, and therefore it can be factored by some object in our set. Remember that AI is a set. Well, then all those morphisms here from that thing in the set doesn't give yet any kind of reflection, because it's a reflection onto it's a weak reflection onto the I, but the I are things of bounded rounds, so that's not what you want. If you work on these things, you know that you can easily produce even reflection onto things of bounded rank. But we're producing a weak reflection onto something of bounded rank, and now if I claim that you can lift this to the full category D, to all the objects in D, simply with the trick that maps. Now it's where semi-weak things. So since we took all the maps into products, there are projections. So xj is simply a larger product than xi. If j is bigger than I, there is a projection. So if there is a projection, we have a chain. We have a chain going down. We have a chain of projections going down, and those projections are not, they are mapped, it's not empty sets. However, now we can ask whether there is any arrow going higher enough, at least for every object. So in order to obtain a weak reflection onto the full class D, it suffices to find an ordinal such that for all the larger ordinals, the corresponding map can be factored through the ith state. Well, suppose you can't. Suppose you fail to produce a weak reflection onto D, then you get a sequence of ordinals branching the indices over all the ordinals where this is always empty. If you fail to get the weak reflections onto D, then you get a chain which contradicts semi-weak Vopenka. This contradicts semi-weak Vopenka because there are maps going down because they are projections, and now there are no maps going up. This can't happen in a locally presentable category. And of course, if M is locally presentable, then the comma category is also locally presentable. Therefore, the semi-weak Vopenka gives a neat proof of weak reflectivity, and is essentially Adamic Rosicky. There's nothing really new here. Now we have to correct semi-weak Vopenka, to correct a weak reflection into reflection. Now, the argument that I sketched gives a weak reflection. Now you want to turn it into a reflection. Then let me do it for a spectra, and then you will see what I'm using, which is essential of a spectra. We already obtained a weak reflection onto the orthogonality category using semi-weak. Now you want to turn a weak reflection into a reflection. Well, people in category theory also know that this is a standard. You can always do that. You can always turn a weak reflection into a reflection. Now we skip the argument. I don't. The argument is really technical, but it's well known in category theory. I think it's already in the book by Bourse, maybe left as an exercise. Actually, what you need from the category is that idempotent split. The trick is using the fact that idempotent split to turn a weak reflection into a reflection. That's the story. Of course, that's why I use the spectra. In the category, in the homotopy category of a spectra, idempotent split. So if idempotent split, you can, by a standard method, correct the weak reflection into a reflection. You make unique that diagonal arrow, which was not unique, you can make it unique using the fact that the idempotent split. Well, then we are done, because we have semi-weak Vopenka implies weak reflectivity, idempotent split implies reflectivity, so we already know. But now this is half of the story. We know that semi-weak is enough to imply reflectivity, but again, this was known in 1993, so that's not really new. And by the way, for simplicial sets, then you don't have that idempotent split. That's a small technical thing. You don't have that idempotent split in the category of simplicial sets, not even if you assume that they are pointed. But that's a nice trick. They are connected. and pointed, then the homotopy category has a splitting idempotent. Okay. The same argument works. And then we know that, but that's not our model category. But it's something like 3 pages in our paper. It's a bit technical, but you simply correct what I showed you for a spectra. You correct it for spaces by playing with base points and connected components. You can do that. So again, semi-weak implies reflectivity in the homotopy category of either pointed or unpointed simplicial sets. Every class of maps. Semi-weak implies reflectivity of every class of maps. Good so far. Yeah, well, again, there is nothing really new here. Cohomological localization is a special case. But now we are going into the kind of problems which I will mention at the end of my talk as being open problems even now. So if you work with a spectra, and instead of homology localizations, which were constructed by Bausfeld, you want to work with cohomology localizations, which is an open problem. Nobody knows whether cohomological localizations exist in simplicial sets or spectra. Nobody knows it. And we know that semi-weak Vopenka implies reflectivity. Actually, this is a longer story. It was long known even before that Vopenkas did it. Now we know by the argument that semi-weak does it. Let me advertise another paper which I published with Joan Bagaria, Adrian Matthias, and Gutierrez in 2015, that supercompact cardinals are sufficient. So if you're interested in getting cohomological localizations, assuming supercompact cardinals is enough. And supercompact cardinals are much below Vopenka. Actually, if you are interested in set theory, I can tell you more about the relative positions of supercompact cardinals, just to understand. I mean, the relation of supercompact cardinals with cohomological localization is much more transparent for the reasons that I may say in my last slide. This is what was known before Trevor Wilson. Of course. Well, actually, there was a small piece of information that you should know, which is the work of Adam Przeciecki. Maybe you know that, maybe you don't know. The work of Adam Przeciecki, already also 2010 for group and 2014, is that if you negate with Vopenka, then you can construct non-reflective orthogonality classes, either of groups or abelian groups. The proof is easier for a group than for a abelian group, but it's really a technical, complicated paper that is a little bit easier to follow. And both come from an earlier result of Adamic, Rosicky, and Kova, saying that under the negation of Vopenka, you can obtain a non-reflective orthogonality class of graphs. Then somehow, well, it goes in the opposite direction. What you want to do is not embed groups into graphs, which would be easy, but you want to embed graphs into groups. You can't embed them graphs into groups, but you can almost embed. So what Adam Przeciecki says is about almost embedding of graphs into groups or abelian groups, and then enough to construct his example. And his example is the clue of the reverse of our theorem. So using Przeciecki, we prove that under the negation of weak Vopenka, there is a class of maps between simplicial sets such that this localization does not exist. Is we use the negation of weak Vopenka. But now we know that semi-weak implies existence, and now weak Vopenka implies a counterexample. And by Trevor Wilson, semi-weak is the same as weak. So we close the gap. Weak Vopenka is exactly what you need for reflectivity, because you have a positive result with semi-weak and you have a counterexample under the negation of weak. And well, basically that's my talk. So you see, after all, it's not that substantial. Well, here's the proof. Here's the proof, but this you can do. You simply use the fact that the category of group fully embeds into the homotopy category with Eilenberg-MacLane spaces. Again, you can skip the details. Once you have a class of groups which is not an orthogonality class of groups which is not reflective, you immediately get a class of spaces which is not reflective in the homotopy category using a full embedding of groups into homotopy types. This was already observed by Adam Przeciecki himself. That's the argument. So using a non-reflective orthogonality class of group, you get a class. Actually, take the Eilenberg-MacLane spaces, and you remember the double pair. Remember the double pair. You saturate it twice. Saturating it twice yields non-reflective subcategory of the homotopy category of simplicial sets, therefore contradicting my previous theorem. But I don't contradict it because to get such orthogonality class of groups, you have to assume the negation of Vopenka. That's for simplicial sets. And of course, the conclusion is what I said. There is an equivalence between weak Vopenka because that's what I said before. By Wilson, weak is equivalent to semi-weak. And to do the same thing for spectra, I just repeat the previous argument. But now, since we use a spectra, we work with the homotopy category of a spectra. And now what I need to do is to embed a billion groups into spectra. Well, again, you take Eilenberg-MacLane spectra, that's a nice fully embedding of a billion groups into the homotopy category of a spectra. So again, having a non-reflective orthogonality class of a billion groups gets a non-reflective full subcategory closed under fibres and products, closed under fibres and products, because any double perp, those categories are double perp. Any double perp, maybe I go one slide behind, the class which is not reflecting is a double perp of objects. This is an example in the stable case of a semi-colocalizing. So when we go into spectra, things of that kind are semi-colocalizing, but not colocalizing. Remember, a double perp of objects doesn't have to be closed under triangles. It's just half closed. So for spectra, what we are producing is a class which is not reflective and it's closed on fibres and products. That's what we get. Now we can ask things. We can ask things. Yeah. Well, sorry. This. Now I'm going to ask. Now I'm going to ask questions in a moment. But here I'm just putting a summary. I'm just putting a summary. The statement that every full subcategory closed under products and fibres, as I said, of any stable local presentable category is equivalent to the weak Vopenka principle. That's exactly what I announced in my abstract. So what is the argument? Using semi-weak, then you get a weak reflection. Then, since I import, that's important, in every triangulated category with countable products, if it has locally presentable models, we are in this situation. We are in this situation. Every simulated category with countable products has idempotent splitting. That's one of the pieces in the argument. So idempotent splitting is what helps us turn big reflection into reflection. So one direction is automatically true for triangulated categories with locally presentable model. And for the converse, the negation of weak Vopenka yields a non-reflective orthogonality of a billion groups, and this gets, as I said, a double perp, which is closed under products and fibres, and a reflection onto that would imply a reflection onto A in groups, which is a contradiction. So this is basically the end of the result in my talk, just putting all the pieces together, which I mentioned, most of which were old, except for Trevor-Wilson. So the only novelty in what I said is the use of Trevor-Wilson's theorem to close the gap. Yeah, now I want to finish with questions. I want to finish with questions, and this will help, so to say, understand hopefully what we proved and what did not prove. I didn't prove that the statement that every colocalizing category is reflective is equivalent to the weak Vopenka principle. And I'm sorry about that, because that's probably what you would like to hear. It would be nice to know that reflectivity of colocalizing subcategories is equivalent to weak Vopenka. Actually, in my paper with Javier and we prove that under Vopenka, colocalizing subcategories are reflective. But the fact that that statement is equivalent to weak does not follow from what we did before. Why doesn't it follow? Because our example, so remember that the second implication was using an H perp class. We have an H perp class where H was precisely a class of Eilenberg-MacLane spectra. That class, as I said, is closed under products and fibres, but not under cofibers. Therefore, I don't have a counterexample. But the reverse implication, which I told you 5 minutes ago, doesn't produce a colocalizing subcategory. And you would say, okay, that's a minor technical thing. I'm sure you can, maybe you close your category by triangles and then you are that. No, it doesn't work. It doesn't work, and now I'm telling you basically why I think this is a difficult problem. I go back a moment. Simply, here, by doing these kinds of things, that's it is a full embedding. You really the homotopy classes of map between Eilenberg-MacLane spaces are just a Homs in group, and the same happens with the spectra. The same happens with the spectra. If you take homotopy class of maps between Eilenberg-MacLane spectra, we just get Hom. That's why there is a nice correspondence between homotopy reflectivity and algebraic reflectivity. However, if we take our target class and we close it in there, the triangles, then it's not enough to take into account map between two Eilenberg-MacLane either spaces or spectra, because then you get in the second component and you get in addition to Hom. That's the problem. So when you want to compute homotopy classes of map between possible suspensions of Eilenberg-MacLane spectra, that's much more complicated. Even if you work with coefficients in a ring, you are getting here the full complexity of the rough category of the ring. It doesn't work. So we are working with a Boolean group that only Z, but that's enough to leave this as an open problem. If you close naively these and the triangles, then simply the argument breaks down because it's no longer a full embedding of abelian groups into spectra. It doesn't work. It doesn't work. So I don't know if this is a difficult problem or not, but somehow that what still remains open is equivalent to other kinds of problems that we discussed many times with Rosicky and other people. So I believe this is not totally immediate. Let me go back to say what I proved. So, for calculating the products and fibres is reflective. That thing is equivalent to weak Vopenka. But if I change closed underproducts and fibres by colocalizing, it's open. So if you have an idea, just tell me. And of course, I know that some of you, I don't know why, I think that when I do this in Zoom, my hand is raised, and I got here something as if I think this is my own hand, sorry. I know that you will raise hand and saying, what are the duals of all these? So I answered this question already before you asked me. What about if you put localizing and then you are looking for co-reflections? So my paper with Rosicky and Gutierrez, which depends on Vopenka, is symmetric. So you get the same results for co and without co. But here's not the case. All what I explained was for reflections. You don't get the same arguments if you work with co-reflections. Of course, again, there should be easy ways to repair that, but we have not done it. And we have not done it. If you have an idea of how to, if you have an idea of how to put here co-fibres and co-reflecting and hope to get the same result, I'll be happy to talk with you because I have not written that. And I don't know if it's easy or difficult. And the last problem, which is related to that, is I mentioned cohomological localizations a moment ago. I said that under weak Vopenka, you can prove that they exist, but I told you that super compact cardinals were enough. And you say, okay, I don't understand with Vopenka super compact. Well, actually, what I wrote here is an open question. And I would say is maybe the most challenging open question I would have on my desk at this moment. The existence of homological localizations. I prefer to work with the spaces you can, equivalent to some large-cardinal principle. I don't know. And I can prove that the existence of cohomological localizations is not equivalent to the weak Vopenka principle. So this is related to, I was asking before, the colocalizing. Of course, if you work with cohomological localization, the class of local objects for cohomology localization is colocalizing. So that question is related to the one which I was asking a minute ago. And the reason why the existence of cohomological localization is not equivalent to the weak Vopenka is that you can prove it with weaker things. So now, Joan Bagaria, my set theory co-author, also wrote a paper recently with Trevor Wilson, the one who proved that equivalence between weak and semi-weak, and they proved essentially that the proper class of strong cardinals is enough to guarantee the existence of cohomological localizations. But that's not what they proved, but actually they that somehow a strong cardinal is enough to get reflectivity of things which are definable with formulas in the language of theory of complexity sigma 2. And I can prove, I will not do it now, that the cohomological acyclics have that kind of complexity. So for cohomological localizations, you have a weaker large cardinal axiom which implies it. So it's not equivalent to weak Vopenka. Is it equivalent to the existence of strong cardinals? I don't know. Is it equivalent to some specific large cardinal principle? I don't know. So basically, I told you what I do know, and I told you what I don't know, and then I'll be happy, of course, to answer any query that you might pose. Thank you very much.
Thank you, Carlos. Let us all give the speaker a round of applause. Right, if you have any questions for the speaker, you can ask them now.
Can you replace the homotopy category of spectra by the derived category of abelian groups?
That's a very interesting question. That's a very interesting question. No, yeah. Let me write it because it should work. It should work. It should work. Well, I mean, okay, yeah, no, it should work. Essentially, let's see. Yeah, here. No, but that's only part of it. Where did I say the if and only if? Here. Yeah. So certainly the derived category of Z has locally presentable models. So you know that semi-weak Vopenka will actually it also idempotence split. So it will give semi-weak, hence weak Vopenka will give reflections in D of Z. Now the question is whether Pietsky's examples give the converse or not for the derived category of abelian group. There is a paper by Don Stanley and co-authors which comes to my mind, which maybe this was done. Maybe this was done. So I tend to think that it's done, but it's true that we don't mention it in our paper. I think it's done, but let me check it. So the only thing is to see if that counterexample also gives a counterexample of the reverse implication. Now I'm not 100% sure, but I think it does. Thank you very much.
Thank you, Leonid. Any other questions?
Yes.
Please.
Actually, I had two questions, but the first one was asked by Leonid. So, so the second question is just a curiosity. If you know if there's any relation between the Vopenka's principle and inaccessible cardinals.
No, wait.
Because it seems that with inaccessible cardinals you can have plenty of colocalizations.
Oh, maybe I didn't. I should have informed more about that. You know that large cardinals form a hierarchy. Yeah? They form a hierarchy.
Yeah.
It means that each large cardinal somehow implies the consistency of the ones which are below. Yeah. And in my understanding, so the inaccessible, people call strongly inaccessible, are somehow the bottom of the tower. So everything that you can state and everything which was mentioned in this talk are above. So somehow the strong cardinals are stronger than the existence of a strong cardinals is stronger than the existence of inaccessibles. Then it comes certainly weak Vopenka, then it becomes super compact, then it would come Vopenka. And then in between, of course, there are many other things that set theories know. Yeah? So in a sense, assuming only inaccessible cardinals, I don't know how to prove any reflectivity theorem. I don't know, because the lowest thing so far in print is a strong cardinal. With the strong cardinals, we can prove reflectivity of sigma 2 definable classes, which include, for example, cohomological localizations. So if anybody in the audience knows something weaker than a strong cardinal yielding reflectivity of some kind, I would be happy to know it.
Well, thank you.
Thank you, Leo. Any other questions? Let's see. So I had a question. So in your 2014 paper with Gutierrez and Rosicky, you had this result that followed as a corollary of your main theorems there, that if we assume the Vopenka principle and we take T to be a triangulated category with a combinatorial model, then all semi-localizing subcategories or all semi-colocalizing subcategories were part of T structures. Now, am I correct in understanding that in this result, even with the new developments, we can't replace Vopenka with weak Vopenka?
Tell me again, sorry, which result? Which result?
I think the result said if the Vopenka principle is assumed, then all semi-localizing subcategories and semi-colocalizing subcategories of triangular categories with combinatorial models were parts of these structures.
Can
Can I replace Vopenka with Vopenka? That's my question.
No, yes, of course. No, because I mean, I have to check the paper, but typically everything that we proved, no. Let me organize a bit better. In that paper, we have theorems about reflections and theorems about co-reflections. The co-reflectivity part, I don't claim having new results, because all that I mentioned in my talk was getting first a weak reflection and then correcting it. Maybe you can do that in the co-case, but I just don't know how. So let's stick to the localize, to the co-localizing, to the localizations. Let's stick to that. Then everything that we did in that paper in 2014, we didn't need Vopenka. Semi-weak was enough. We didn't say at the moment. We could have said it at the moment, and that's what I did in my talk. Everything in that paper can be done with semi-weak. And now, thanks to Trevor Wilson, that's the really new thing, weak Vopenka is enough. So the answer is yes. Everything we do there with Vopenka on the co-localizing part, weak is enough. But on the localizing part, it's open again. It's what I said. If you can work out the duals with these techniques or others, I would be happy to, maybe you can write me and we write a joint paper.
Sure. Thank you. Any other questions? Well, if you have no more questions, let's thank Carlos once again. Yeah. Thank you.
Appreciate your attendance.
Thank you all for coming. We have Maxime Ramsey next week. Yeah, Mr. Yeah,
Thank you, Carlos. Thank you.
Thanks to all of you.